then short time Fourier transform, then wavelet transform, then we will go for empirical mode decomposition. So for Fourier transform to empirical mode decomposition, this journey will be explained. And we will see what the limitations existing in the EMD method and the motivation for development of new method, empirical wavelet transform. And then we go for Fourier-Bessel series expansion and what are the actually advantages of Fourier-Bessel series expansion, that also we will see. And then Fourier-Bessel series expansion based empirical wavelet transform that we will call as a FBSE EWT. That will also actually that will be explained. And after that we will see glaucoma diagnosis based on the fundus images, and we will use this two-dimensional version of the Fourier-Bessel series expansion based empirical wavelet transform for getting sub images, and sub images they will be used to extract the features, and then based on the features this automated classifying systems will be developed, and in the end conclusion will be provided. So transform actually, that is a very common term. If you see actually in all areas of actually science and technology, you will find the use of transforms. You will not find any area where these actually transforms are not studied, whether it is physics, chemistry, mathematics, mechanical engineering, electrical engineering, computer science. You will find in most of the areas these transforms are applied, and they have nice applications. So this transform, what it does actually, it is a mathematical operation, and which converts a function we can call also a signal, or sometimes when it's discretized, then we call it sequence, and that is actually one domain, and it converts into another domain where we can have function, we can have sequence, or that is other domain. And so one of the actually nice example of transform, that is Fourier transform. So we can take a signal from time domain to frequency domain, and it is like a bridge between two domains, time domain and frequency domain. And by doing this transformation, we can go from one domain to other domain. And there are some certain actually advantages, and certain processing of the signals can be done in transform domain in easier manner, in effective manner. So due to that, we prefer to use this transform domain for this processing of the signals. And once it is done, then we come back in the actual domain or time domain, and that is actually the process. So this is like we use two operations. One is analysis, and second one is synthesis. So that we will see in the detail. And why we need actually signal transforms, there are certain reasons. So these are the actually few applications or advantages of the transform. Transform provides hidden information about the original function or signal, like what are the frequency components present in the signal, what is the strength of the different frequency components in the signal, which frequency is the major frequency, and which frequency is the minor frequency. So such kind of actually analysis can be done in the frequency domain, in the transform domain. That is not actually possible in the time domain. Time domain tells us what are the different values of the signal at different points of time. But when you go in the frequency domain, it tells us what are the different values of the frequencies, or what are the frequencies present in the signal that is clear from the frequency domain. And the transform actually helps us to solve differential equations. So in signal processing, we generally assume that these signals are actually output of the system, and it makes sense also. So when you assume that signal is generated by a system, for example, like a speech signal, which is the output of the vocal tract, electrocardiogram, ECG signal, which is the output of heart system, and electroencephalogram, EEG signal, which is the output of brain system. So these actually, when you use these systems in order to have this kind of signals as output, then we use some mathematical models to represent the system. So this differential equation is one of the actually a model where we represent system with the help of input and output by using differential equation framework. And in order to solve this system, in order to perform analysis, we have to solve this differential equation. So that is actually done by the transforms in easier manner. And this may be like Laplace transform, we use Fourier transform. And nicely manner, we can solve them and we can solve the differential equation. So indirectly, we are solving the system, we are understanding the system. And that actually understanding help us to have a lot of interpretation of the signal of the, and can be used for the diagnosis purpose. And this transform may provide data compression, and storage may require less memory. So like the signal transforms require design of basis functions. And if somehow if you are able to use basis functions similar to the signal that you want to analyze, then in that way, the requirement of coefficient in the transform domain will be relatively less. So that is like the selection of the spoon depends on the type of food. For example, if you want to have actually food like noodles, and noodles are actually discontinuous food, complicated. And in order to handle noodles in effective manner, we go for fork, because fork is also discontinuous spoon, and food is also discontinuous. So in that way, nicely we can handle such kind of food with the suitable spoon. So same thing actually in the transform, if you can design the basis functions according to the signal that we are analyzing, then the requirement of coefficients will be less in the transform domain. And some operations may be easier to apply in the transform domain. For example, like convolution operation in linear time invariant system. So convolution, when you are implementing time domain, and then you have to assume causality of the system. So causality, and if you are going in transform domain, then actually one of the beauty of the transform, there is no time in the frequency domain and time domain, they are mutually exclusive, that we will see in the coming slides. And by going in frequency domain, you don't have time in the frequency domain. So this frequency domain processing doesn't depend on the time domain. So you don't need to assume any condition on the time. So this is actually one of the major advantage of the transform domain. We can do a lot of processing and without depending on the time domain. So this convolution, for example, in time domain can be implemented as a multiplication of the frequency domains of these two signals. And the signals may be like if you are implementing convolution with the LDA system, so that one may be the input signal and other may be the linear time, that impulse response of the linear time invariant system. So you just multiply the spectrum of these two signals, and then multiplied spectrum can be converted back by using inverse transform or synthesis process in the time domain. And in that way, nicely you can have the convolve output or convolution output of the convolution of the signal to this system. So these are the some advantages. By that actually there is a lot of scope of the transforms in the area actually in various applications, and these transforms are also very useful for machine learning algorithms that we will see. These transforms can decompose this complicated signal in terms of simple components, simple signals, where nicely we can extract features. And these features can be used for training the system for classification purpose, that we will see in this talk. So the first transform, that is a Fourier transform that was proposed by Fourier in 1807. So according to this Fourier, this complicated signal can be represented with the help of simple signals, basic signals. So Fourier Fourier was from France, and he was from physics background. And Fourier his father was tailor, not mathematician, tailor by profession. And he was was poor, and his parents died when he was 4 years old. And this Fourier used to work in hostel, and that old time there was no electricity, and people used to use candles for study purpose, and they used to throw the remaining part of the candle outside. In this Fourier used to collect these pieces of the candles in the daytime, And when everybody was sleeping, Fourier used to study. And this is Fourier actually, he joined defense, and from the defense he came to Ecole Polytechnique, and where he was working on the prism. And this prism actually, he observed that this white light can be decomposed into 7 colors, basic colors. So he got idea, and he said that if white light can be decomposed, then similar way, this complicated signal also can be decomposed into simple components, simple signals. So that was the idea, and he represented this actually complicated signal in terms of simple signals like sinusoidal functions. So according to actual this Fourier, an arbitrary function is continuous or has finite number of discontinuities can be defined in finite interval with the help of arbitrary continuous graph. With the help of sinusoidal functions. So this graph can always be represented as sum of sinusoids. Sinusoidal functions can be used to represent this complicated signal. So this Fourier transform, we can actually represent these complicated signals in terms of simple signals. And these simple signals, we call them basis functions, and they are sinusoidal functions. And we have seen this Fourier transform is like a bridge between time domain and frequency domain. And time domain tells us what are the different values of the signals at different points of time. And frequency domain tells us what are the frequencies values at different what are the different frequencies present in the signal. Information can be obtained by the frequency domain. And this time domain to frequency domain mapping can be obtained by the analysis process, and frequency domain to time domain processing or mapping can be obtained with the help of synthesis process. So this analysis and synthesis equations for Fourier transform can be represented mathematically, that you can see in this slide. And this first one, that f omega equals to integration of ft e to power minus j omega t dt, that is known as analysis equation. And ft equals to 1 upon 2 pi integration of f omega e to power j omega t d omega, that is known as synthesis equation. So this analysis equation, we are integrating actually time from minus infinite to plus infinite. So there is no time in the frequency domain. You can see we have integrated entire time. So frequency domain is actually has only information about the frequency and no information about the time. Similarly, when we are doing synthesis process, then we are integrating frequency from minus infinite to plus infinite. So by doing this processing, this entire frequency is integrated. So there is no frequency in the time domain, only time information is available. So this time domain and frequency domain, both whatever we actually obtain, they are mutually exclusive. Like when you are in time domain, there is no frequency domain information. And when you are in frequency domain, there is no time domain information, because both are mutually exclusive. And this is one of the example where you can see this actually in left hand side, you can see the signal, 3 sinusoidal functions, 5 Hertz, 25 Hertz and 50 Hertz. And when you apply Fourier transform, then you can see peaks in the spectrum, that 5 Hertz and 25 Hertz and 50 Hertz. So this Fourier transform tells us actually what is the major frequency present in the signal. So in first case, you can see this peak at 5 Hertz, second case peak at 25 Hertz, and third case peak at 50 Hertz. So this actually, also Fourier transform also measures the similarity between the design basis function and that basis function with the signal. If it is present in the signal, that particular basis function, then according to that frequency will be having peak in the spectrum. Otherwise, this peak will be absence. So that will be like a frequency strength of that particular frequency component will be 0. So in that way, Fourier transform tells us what are the frequencies present in the signal and different strengths of all the components, frequency component present in the signal. And one of the major actually the shortcomings of the Fourier transform, that this Fourier transform is able to identify all frequency components present in the signal, but because that we have seen, when you are integrating time, then there is no time in the frequency domain. So frequency domain actually doesn't have any time domain information. In other words, this Fourier transform based representation doesn't provide any information about the time localization, or what time these frequencies are present. It tells us only what are the frequencies present in the signal, but it does not tell us at what time these frequencies are present. So that time information is actually not available in the Fourier transform based representation. And this time domain based representation that is actually is required for non-stationary signals. So based on this time varying nature of the signals, we can classify signals into two classes. One is stationary class of signals, and second one is non-stationary class of signals. So stationary signals, actually signal processing, we use mathematical models to represent the signal, and if the parameters of the models, they are constant with time, then we call them stationary signals. If any of the parameter of these models change with time, then we call them non-stationary signals. And it is very difficult in this world to find stationary signals. So stationary signals actually consist of frequency component. They do not change with time. So for such kind of, since they are not changing with time, so you don't need time information. And the Fourier transform works well for such kind of signals. And non-stationary signals, actually, they include time varying frequency components. So Fourier transform is not suitable for such kind of signals. And for such kind of signals, we need to determine time localization of frequency component. So that is actually, that is one of the motivation for going for time information in the Fourier transform. So that Fourier transform will be suitable for non-stationary signals. So this is actually one example here we will see that is for stationary signal and non-stationary signal. And first signal that is actually has three frequency component. It is a superposition of three sinusoids, 5 Hz, 25 Hz, and 50 Hz. And when you see the these all three frequency component, they're present at any point of time. So this is one example of stationary signals. And when you take a Fourier transform, then you can see right hand side, it has three peaks, one at 5 Hz, second one at 25 Hz, third one at 50 Hz. And when you go for other case, non-stationary signal, all these frequencies are present, but they are present at different points of time. So for example, 0 to 0.3, 5 Hz frequency is present, and 0.3 to 0.6, 25 Hz frequency is present, and 0.6 to 1, then this is actually 50 Hz frequency is present. So this is concatenation of these three frequency components, and that is actually example of non-stationary signal. And when you apply Fourier transform for actually these stationary signals and non-stationary signal, non-stationary signal, then you see we get the same spectrum for both cases, for stationary signal and non-stationary signal. And so this actually, in both cases, it tells the only three frequency components are present. But when you see non-stationary signal, we also need time information together with three. Then only this interpretation can be done. So when you are classifying signals as stationary, non-stationary signals, then this Fourier transform actually is a misleading. Fourier transform is not actually suitable for unique representation, because this frequency domain can be corresponding to stationary signal, and that can be corresponding to non-stationary signal. So this Fourier transform is not unique representation when you consider signals as stationary and non-stationary signals. So this is actually one of the motivation for time frequency representation, so that we can include this time information together with frequency representation, so that this representation will be suitable for non-stationary signals. So the way of looking such kind of representation is the actually nature of the basis functions. So like basis functions that we use in such kind of actually representation, like in Fourier transform, these are sinusoidal functions, and sinusoidal functions they extend from minus infinity to plus infinity. They are periodic in nature, and due to that, actually, its spread is infinite, and the resolution is proportional to 1 upon spread. So like they stretch into infinite in time. So due to that, actually time localization and time resolution and time concentration will be 0. And this instantaneous, actually, when you see these signals in frequency domain, they have impulses in frequency domain. They are impulsive in nature. So due to that, spread is actually 0 due to impulses in the frequency domain, and it has infinite frequency resolution, infinite frequency localization. So this Fourier transform based representation, when you see from basis functions point of view, it has got very good resolution in frequency domain, very good localization in frequency domain, and very poor localization in time domain, or nearly 0 localization in time domain. So actually we have seen non-stationary signals, they actually change with time. Whatever models you use to represent non-stationary signal, they also change with time. So in order to have this time varying information, we need to include time domain component also together with the frequency domain component. That is also one of the motivation for time frequency representation. And that is also known as time varying frequency analysis, time varying spectral analysis, time frequency distribution, time frequency analysis. There are various names for this representation. And the first technique actually that is useful for non-stationary signal that were developed, that was based on the Fourier transform. And Fourier transform actually gives you global analysis that is for minus infinite to plus infinite. And what in STFT, short time Fourier transform, actually we do, we divide the signal into different segments, and each segment we assume that signal is stationary, and then we apply Fourier transform of each segment, and then the arrangement of these Fourier transform gives us short time Fourier transform, that is known as STFT. So here you can see this is the mathematical actually equation for computing short time Fourier transform, STFT, and XT the signal that we want to analyze, and WT the window function, and T that's the shifting parameter. And by choosing different T dash, we can move window from one point of time to other point of time. So in that way, actually signal can be multiplied with the shifted window, and we can have actually a windowed signal at different location, different points of time. And then you apply this Fourier transform kernel, multiply with this e to power minus j omega t, that is similar to Fourier transform. And here you can see by using this window, it introduces another parameter, that T dash. So that is actually center of the window, and this gives you time information. And this window is actually localized in time. So after some time, this window will become 0. So that will give you nice localized part of the signal, and then we can compute its Fourier transform. You can get the spectrum frequency information for that particular location, particular window signal. And then different T dash, and then in that way you can have frequency information or the spectral components for entire signal from the beginning to end, from the 0 to infinity theoretically. So this here you can see there are two. Now this is shifting in time, and this omega parameter that actually helps us to shift in the frequency. So with the help of this window and this Fourier transform kernel, we are able to cover the different areas in the time frequency domain. And that is actually now basis functions, like earlier Fourier case, these basis functions were having actually different regions in the frequency domain. So different spectral lines in the frequency domain. But here in each of frequency domain, now due to use of window function, you have actually one kind of rectangular window, or different rectangular regions, or there's tiles, or kind of tiles in the time frequency domain. And each tile, the shape and this different actually height and width of these tiles will be determined by this window function, and the shifting, this omega will determine its location, T dash and omega will determine its location. So based on that, when you solve this integration, then in left hand side, if you can see, the short time Fourier transform will be function of two parameters. One is time parameter, and second one is frequency parameter. So here you can see this short time Fourier transform STFT that is actually mapping from time domain to time frequency domain. And that Fourier transform, it was mapping from time domain to frequency domain. And there was only one kind of sequence you have, like you have discretized signal, then time domain sequence, one-dimensional signal. It will be converted into one-dimensional signal in frequency domain. But here, this is one-dimensional signal will be converted into two-dimensional representation. That is actually short time Fourier, that is time frequency. So now your signal will be a function of time and frequency in time frequency domain. So that is actually the idea of time frequency representation. And that converts actually in one way signal into two-dimensional signal. One-dimensional signal will be converted into two-dimensional signal, that is STFT. This is one of the example that you can see that different like value of t dash equal to -8. So it will cover the initial part of the signal and other parts will be 0. So when you apply Fourier transform, then this part will be transformed by using Fourier, and you will get the frequency component corresponding to this part only. When you shift it t dash -8 to -2, then you will get the frequency components, this information from the middle part of the signal. And then again, by shifting t dash equal to 4 or t dash equal to 8, you can have different actually, different regions will be isolated from the signal. And then you can apply Fourier transform, and then it will give you the spectrum of different regions. And then arrangement of these spectrums gives you short time Fourier transform STFT. And this short time Fourier transform, that is actually, it is a complex quantity. So for representation purpose, we use square magnitude of the short time Fourier transform STFT, that is known as spectrogram. So here you can see this is the example of speech signal when you speak MATLAB. So this is the signal actually time domain. It looks like this pattern when you speak MATLAB. And there are two types of actually spectrogram. It depends on the size of the window. So when you have a large window, for example, its size is 256 samples, then resulting spectrogram will be known as narrowband spectrogram. So when you have large window in time domain, and due to Heisenberg uncertainty principle, it will have narrowband nature in the frequency domain. Similarly, when you have short window in time domain, then it will have wide band in frequency domain. So this is actually, suppose you have short window of that 64 sample size, then resulting spectrogram will be wideband spectrogram. And here you can see the upper spectrogram, that is actually example of narrowband spectrogram. And this lower one, or this bottom spectrogram, that is example of wideband spectrogram. So here actually you can see the resolution, the concentration, focus, that is proportional to the 1 upon spread. It is inversely proportional to spread. And here you can see when you have narrowband spectrogram, then actually corresponding to that you will have good resolution in frequency domain. So first one, upper one, narrowband spectrogram gives you very good frequency resolution. And in this spectrogram, one can identify different frequency components present in the signal. Like when you talk about the speech signal, then you can identify nicely what are the different formats present in the signal, what are the different resonances, and that nicely can be identified. On the other hand, if you go to the bottom spectrogram, that wideband spectrogram, there you can see these actually, there are blurring kind of phenomena is happening. These formats are merging to each other. And that is actually, that is not a good resolution. So that wideband spectrogram, since wide area is wide, and by nature of the spectrum is wide band. So due to that, resolution is poor in the frequency domain. So the upper one, that is actually narrowband spectrogram, which help us to identify these frequency component formats present in the signal with good frequency resolution. So actually there are certain shortcomings of the short time Fourier transform. Short time Fourier transform that we have seen, we require window function And by using the shifting concept, we cover actually signal from the beginning to end, and that is sliding window function. And what is the size of this window and what is the type of the window? That is not clear. There is no thumb rule which will suggest us for a given signal what should be the size of the window and what should be the type of the window. And when you have actually size of the window, for example, wide in time domain, it gives you poor time resolution. On the other hand, in frequency domain, it gives you good frequency resolution. Similarly, when you have narrow analysis window in time domain, it gives you good time resolution. On the other hand, in frequency domain, it gives you poor frequency resolution. So the size of the window actually that affects the resolution, and type of the window is also actually not clear for which kind of signal, which type of window is required. So these are actually the problem shortcomings of the short time Fourier transform. These are the major issues when you use short time Fourier transform for signal analysis or spectrogram for time frequency representation or time frequency basis functions based decomposition. So there is actually this use of window is also actually associated with the Heisenberg uncertainty principle. So that like it says delta t into delta f is greater than or equals to 1/4 pi. So delta t, that is actually spread of the signal in time domain, and delta f is the spread of the signal in frequency domain. So delta t is also known as duration of the signal, and delta f, this is also known as bandwidth of the signal. So the duration and bandwidth product, that is actually bounded by some fixed number 1/4 pi. So for this Gaussian signal or Gaussian kind of window, this equality is there. And for other kind of window function, there is inequality. So this is, you cannot actually arbitrarily reduce delta t or duration of the signal. Similarly, you cannot arbitrarily reduce the bandwidth of the signal. So if you reduce duration of the signal, then actually delta f will increase, bandwidth will increase. Similarly, if you increase the bandwidth delta f, bandwidth, then delta t will also increase. So this it is very difficult to minimize both delta t and delta f together, because if you minimize one, other will increase. If you minimize second one, then first one will increase. So delta and delta bandwidth and this duration product, you cannot minimize both of them to an arbitrary value. So that is actually uncertainty principle, because they both are associated with the uncertainty principle. And in other words, this resolution in both domain, that is proportional to this inversely proportional to duration and bandwidth. So indirectly, if you cannot minimize these two parameters, bandwidth and duration, to arbitrary very less, then it means also that you cannot have time and frequency resolution both very high. So that is actually, these resolutions are associated with the Heisenberg uncertainty principle. So due to that actually reasons, in the literature, this wavelet decomposition was proposed, wavelet method. And wavelet actually is a waveform of limited duration, and which has got an average value of 0. So in case of sinusoidal functions, we are using this frequency concept. Here we use a scale function. So this, according to scale, actually, we can make this window adaptive. So when you see this window at large scale, it gives you a good time, poor time resolution and good frequency resolution. And when you see this window at low scale, it gives you good time resolution and poor frequency resolution. So when you see signal or window at low scale, design window at low scale, that is suitable for the high frequency components. And when you design window at high scale or large scale, then actually it is suitable for low frequency components. So that is the, so different scales can be actually used to design the windows for analysis of different kind of frequency components present in the signal. And the sinusoidal functions, that such kind of actually basis functions we can obtain at large scale. And if you want to have very high frequency impact impulse kind of basis, then we can go for low scale. So by using different kind of scale, one can actually design various windows, and that will be very suitable. Actually, you can change the window. In STFT, once you have fixed the window, then you don't have flexibility to change it. Once you decided the size of the window, type of the window, then you don't have flexibility to change it. But in a wavelet, you have flexibility. You can change size of the window at different scales, and that is actually, that depends on the scale parameter. And you have one mother wavelet, and when you change the scale, then you can have different kind of daughter wavelets that we will see. So here you can see this example. The foods are better handled with a fork than a spoon. So the selection of the spoon depends on the type of food. And if you want to have actually noodles kind of food, then such kind of foods can be handled in better way with the help of fork, because your food is discontinuous and the spoon is also discontinuous. And the wavelet is actually giving you an opportunity where you can design various basis functions according to the nature of the signal. If your signal requires very good time resolution, you can have basis functions of good time resolution. If your signal require analysis of good frequency resolution, you can have basis of good frequency resolution. So different kind of resolutions can be obtained when you use wavelet. So that is why we call wavelet actually has multi-resolution analysis. You can analyze signal with a different scales that will give you multi-resolution analysis. So when you use this wavelet as a basis functions, and then such a transform known as continuous wavelet transform, or CWT, and it overcomes the fixed resolution problem of short time Fourier transform by applying variable length window, and that actually window is controlled by the scale parameter. And we have also seen this analysis window of different lengths are used for different frequencies. Suppose if you have high frequency components present as signal that requires narrow band analysis, and which provide actually good time resolution and poor frequency resolution, and that can be designed with the help of low scale. Similarly, if you want to have wide window analysis, which is suitable for low frequencies and it provides good frequency resolution and poor time resolution, that can be obtained by the large scale. And so based on the selection of different scales, we can come up with a different kind of resolutions, or which are suitable for different kind of frequencies for the analysis. So now it should be clear at this point, this wavelet actually method works well. Wavelet based transform works well if the signal that we want to analyze, it contains both kind of frequency component, low frequency component as well as high frequency component. So then for low frequency component, you can have different kind of scale, and high frequency component, you can have different kind of scales. If the nature of the signal components that present in the signal, they are having either low frequencies or high frequency, then STFT is a good choice. So this wavelet actually is suitable only when the frequency components that you are analyzing, they have different kind of nature than the data that are present in the signals or data. And it may have actually spikes, it may have impulsive kind of nature, it can have sinusoidal kind of nature, it can have short high frequency burst. So different kind of actually signals are present at different points of time. Then actually a wavelet is a good choice. And this is the mathematical representation of this continuous wavelet transform, CWT. And here you can see this XT is the signal that we want to analyze, and the psi-t is mother wavelet. And by doing this shifting by tau, and by using this scale parameter S, we can actually have daughter wavelets. So this psi-t, from psi-t we can obtain 1 by under root S psi-t minus tau by S, that is mother, this is daughter wavelets. And we introduce this normalization constant in the daughter wavelet, and that actually helps us to actually have uniform nature of these basis functions. Whatever daughter wavelets and their energy is actually similar to the energy of the mother wavelet. So each daughter wavelet also can be used as a mother wavelet. So that is actually, we have big library, and where you have a lot of flexibility, lot of scales, lot of shifting parameters. So we believe that at least one basis function when we design it different scales will match with our requirement. So XT, the signal that we have to analyze, and these are the daughter wavelets, 1 by L2 dash IT minus tau upon S. They are obtained from the mother wavelet IT. And when you integrate it, then you can have actually transform domain, left hand side. This is continuous wavelet transform, which is function of two parameters. One is tau and S. Tau is the actually translation parameter or shifting parameter, and that is actually has information about the time. And S is the actually scale parameter, which has information about the scale. And the scale is proportional to 1 upon frequency. So when from the scale, one can get information about the frequency. So when you have large scale, that is indication of low frequency. And when you have low scale, this is large frequency. So in that basis, the CWT time scale representation, whatever we get, so CWT actually converts signal from time domain to time scale domain, or one-dimensional signal into two-dimensional signal. And where is time actually in the scale can be converted into frequency. So this time scale representation also can be used to obtain the time frequency representation. That is actually one of the advantages. And now here you can see this continuous wavelet transform. This is continuous in nature. We will see one example. So this is the signal, and for that we want to actually have this time scale representation, wavelet transform, continuous wavelet transform. So here you can see the signal is a finite, and it has all frequency component present in the signal, because a finite time the duration is finite, so it will have infinite bandwidth according to uncertainty principle. And when you have infinite, then you have all frequency component present in the signal. So when you see this time scale representation, at low scale you have good time resolution because spread is less in time domain. And when you go for large scale, then you have poor time resolution. So that spread is actually more. So this you can see we are able to analyze the all frequency components present in the signal with different kind of resolution. At low scale you have good time resolution. At large scale you have poor time resolution. So that is actually multi-resolution property of the wavelet transform. And low scale, when you are low scale, you need actually this is suitable for high frequency component, and you want to have good time resolution. Similarly, when you are analyzing signal with large scale, high scale, then it requires actually it is suitable for low frequency component present in the signal, where you have good frequency resolution, poor time resolution. So that actually different kind of skills are suitable for different kind of actually analysis of the signals. And this continuous wavelet transform, when you want to implement in the computer, this use of actually continuous variables will require infinite memory. So that is actually, that cannot be processed with the help of computers or machines, because we have finite memories. So in order to implement this continuous wavelet transform, we need to discretize them. These variables are discretized. So this shifting parameter, scaling parameter, we discretize them, and that actually help us to get wavelet transform, dyadic wavelet transform, the discrete wavelet transform, DWT. And dyadic means that is actually half scale. That is the scale changes the half, the dyadic word comes. And that is actually one kind of discrete wavelet transform. And when you convert into discretization form, that gives you dyadic discrete wavelet dyadic DWT. And here you can see this is actually discrete wavelet, and discrete, in fact, discrete daughter wavelet. And that is psi the wavelet, mother wavelet. And when you compute this, then that results you discrete wavelet transform. And this DWT can be implemented with the help of filter bank, that is two-channel filter bank. So that you can see, like say you have signal Xn, Then you apply this signal into low pass and high pass, then downsample by 2. So that upper one actually is high pass filter, downsample by 2, and lower channel, that is low pass filter, downsample by 2. So the upper one gives you the details, and lower one gives you the approximation. So detail is actually high frequency information, and approximation is a low frequency information. So this is one level DWT, decomposition. And again, we can decompose this approximation into 2 parts, approximation detail. So that is actually 2 levels. So now when you decompose this into 2 levels, so then you will have first detail, and then the second detail, and second approximation. So when you are decomposing third level, 2 levels, so then there will be 2 details and 1 approximation. So this is actually basic concept of DWT. And this real life signals, the most of the actually real life signals, this low frequency components actually they are dominant. They are significant part of the signal. So what we do, we always prefer to decompose low frequency part or approximation of the signal rather than details of the signal. So because the details, that is high frequency parts, actually we are not they are not major part. They are not actually dominant part of the signal. So sometimes if you keep this information in the signal or not keep, it doesn't affect too much their quality, because this inclusion of these kind of frequency components in the signal, actually we are not able to perceive them. So like for example, in case of audio signal, if you are including high frequency component or not including high frequency components, there we are not able to perceive that difference. Our ears cannot see, ears cannot listen high frequency component, and similarly our eyes cannot see these high frequency component present in the images. So due to these reasons, we don't include high frequency component in the representation, and that gives the idea of the compression. So like here you can see detail is we are not decomposing, we are only decomposing approximation. So that was the Mallard's idea, Mallard concept. And in that way, you can decompose the signal into low frequency and high frequency components. And again, for example, here we have seen this 2-level decomposition. And from the 2-level decomposition, we can synthesize again this 2-level decomposition, and then you can get signal back. So this DWT, discrete wavelet transform, can be actually considered as analysis synthesis parts, in both parts here. And like Fourier transform, we have analysis and synthesis part. In DWT also, here these 2 parts, like first level, this 2-level decomposition can be considered as analysis part, and reconstruction can be considered as a synthesis part of the transform. So in that way, you can decompose signal up to any level, and then according to your requirement, you can select particular band, you can remove that particular band, you can replace it by zeros also. So suppose this particular band belongs to noise, you can make it 0, you can throw it, and you can remove from the signal, and then you can reconstruct signal back. So in that way, filtering can be done, and various features can be extracted from the different level of decomposition by the different bands, and that can be studied together with machine learning algorithms for the classification purpose. So this is one example here actually, if you see the DWT decomposition for approximation detail. So like the first level, you can see the signal has actually noise, and if you decompose this signal into first level by using this first level decomposition, DWT, discrete wavelet transform, then you have nice approximation and detail. So detail actually belongs to high frequency component, and that is one kind of noise, and that you can throw it, you can remove it from the decomposition, and you can reconstruct signal from the approximation. And again, if you want to decompose this approximation, you can see from the signal it has some fluctuation, some noisy part, that again you decompose into 2 parts, approximate details, and then some noise you will be removed in the form of details. Then again, whatever approximation you get, then again you decompose into approximate details. So in that way, you can filter out the noise and you can reconstruct signal back. So that is actually that help us to denoise the signal, enhance the signal, and signal make close to the clean signal. That is actually that the denoising process can be carried out with the help of discrete wavelet transform. Now, discrete wavelet transform DWT, it has got actually some problems here for a given signal, what level should be used for the decomposition. Like you have seen this first level, we are decomposing signal into two levels, approximation detail. And then again, we are taking approximation, then we are decomposing two levels, approx detail. So what is the number of levels? That is actually, there is no thumb rule which will help us to determine the number of levels required for the decomposition of the signal. And also, it is not known like which mother wavelet is suitable for which kind of signals. So that most of the study actually this is based on the trial and error. They study various wavelets, various mother wavelets, and then they find which mother wavelet is better. So due to these reasons, in the literature recently, notice the 1998, this another transform was proposed that is known as Hilbert-Huang Transform. So whatever transform like till now you have seen this Fourier transform, wavelet transform, they are actually basis functions we are designing from our side. Like you see all signals, whatever signals we represent in the help with the help of basis functions. Like in case of Fourier transform, these basis functions are sinusoidal functions. In case of wavelet transform, these functions are wavelets. But we are designing from our side, and we are representing forcefully the signals in terms of these basis functions. So signal is actually like, for example, your speech signal, whatever signals you encounter in real life, this is not sinusoidal. Like electroencephalogram, EEG signal, this is not sinusoidal, and electrocardiogram, but we are representing these signals in terms of sinusoidal functions, in terms of wavelets. So recently, actually, a new technique developed this for Hilbert-Huang Transform HHT. That is actually fundamentally it is different than like Fourier transform, short time Fourier transform wavelet, where we design basis functions from our side. But here in Hilbert-Huang Transform, you don't need to design basis functions from your side. These basis functions will be extracted from the signal itself. So that is why we call them intrinsic mode functions, IMFs. And this Hilbert-Huang Transform is highly suitable for analysis of non-stationary nonlinear signals. And it has got two parts. One is empirical mode decomposition and second one is Hilbert transform. So empirical mode decomposition helps us to decompose the signal into simple components known as intrinsic IMFs. And Hilbert spectral analysis that actually help us to compute their amplitude envelope and instantaneous frequency. So this method actually, it doesn't have any mathematical framework, but it is based on one algorithm, actually one that is known as shifting process, and it is based on the maxima and minima. You have to pick up maxima and minima, then you have to interpolate them, then you have to average the envelopes corresponding maxima and minimas. Then based on this average, you have to determine the residual from the signal. You have to subtract that part. Then there are some certain conditions of the IMFs, and if this residual is satisfying these two conditions, then we call them IMF. Otherwise, we have to repeat the same process. So in that way, actually, the shifting process is used to determine these IMFs, and this method can be applied for any kind of signal. So whatever signal, whether it's stationary, non-stationary, non-linear, linear, you just give signal and it will decompose into set of components, IMFs. And then Hilbert spectral analysis determines their amplitude, envelope, and instantaneous frequency. So like the sinusoidal functions, we assume that this amplitude and frequency, they are actually constant with time. And in case of Fourier transform, here we allow them to vary with time. So like amplitude and frequency, they change with time of these basis functions that we obtain from the signal itself. So that is what we call them amplitude and frequency modulated kind of waveform, or IMFs, intrinsic mode functions. And this EMD method is an adaptive method. It is data type dependent method. You don't need to design any basis functions here, and doesn't require any condition about the stationarity and linearity of the signal. And it is actually suitable for nonlinear signals. And each IMF should satisfy two basic conditions. like a complete data set, the number of extrema and the number of zero crossings must be the same or differ at most by 1. So this condition ensures that like whatever this basis functions, whatever this IMFs that you obtain, they look like sine cosine functions. And second condition, actually it says the mean value of the envelope, which is defined by the local maxima and local minima, is 0. So it ensures that whatever IMFs you have obtained, that is symmetric in nature. So these signals are these IMFs actually that you determine from the by applying this EMD method. They are symmetric in nature. They are like sine cosine functions. So in the literature, they have considered amplitude and frequency modulated sinusoidal signals kind of pattern. And this is one example. Here you can see this is the empirical mode decomposition of healthy electroencephalogram EEG signal. The electroencephalogram EEG signal actually measures the electrical activity of the brain. And here you can see this is a healthy EEG signal, and these are the obtained IMFs, IMF1, IMF2, IMF3, IMF4, F5, 6, 7, 8, 9, 10, 11, using this EMD method. And this IMF first one, that is corresponding to high frequency component, that is the highest frequency component present in the signal. And IMF 11, that is actually lowest frequency component present in the signal. So these IMFs are arranged from high frequency to low frequency components. And this first component IMF1, this is also known as detail, and that is actually that is a signal that is corresponding to large that low scale, and low scale, that is actually, so that is the highest frequency. Similarly, IMF 11, that is signal is corresponding to large scale, so that is very high scale, so that is lowest frequency component. So this IMF 1 is known as detail. This is the highest like frequency detail, and the IMF 11 the lowest frequency approximation. So in the literature, it has been shown that this EMD method it also gives you this dyadic filtering or filtered versions like Wavelet. So where you decompose the signal different approximation details. And here also, by using this empirical mode decomposition, one can decompose this EEG signal or any other signal into a set of IMFs. And these IMFs actually, they can be considered as approximation details like Wavelet method. But here, you don't need to design actually basis functions from your side, and you don't need to design, don't need to know the level of the decomposition. So this is adaptive in nature, and for a data-driven technique, whatever data you provide, and it will decompose accordingly. And before going for new technique, Fourier-Bessel series expansion based empirical Wavelet transform, let us have just a brief overview of the Fourier-Bessel series expansion. So this Fourier-Bessel series expansion, that actually it has got some advantages over this Fourier-based representation that earlier that we have seen in the beginning of this talk. And it has got actually Fourier-Bessel series expansion, you will call it FBSE, and it has got various advantages, like it does not require use of window function in order to obtain a spectrum of the signal. So like in case of Fourier transform, we require use of window function. We need window function, so that because this what the Fourier transform will be compute for finite signal, it can be considered as a convolution of the sinc function in the frequency domain with the actual spectrum of the signal. So due to that, actually some spectrum leakages are there, and that is removed. These leakages are removed with the help of window function. So we don't need to use, we don't need to require actually use of window function here. Window is not required. And this Fourier-Bessel series expansion actually represents real signal in terms of real Bessel basis functions. So like in case of Fourier transform, our basis functions are complex, and even your signal is real, you are representing the signal in terms of complex basis functions. But here your basis functions are real. And this FBSE helps us to provide actually a representation of real signal in terms of positive frequency. On the other hand, in Fourier transform, you have both kind of frequency, positive and negative. And here the basis functions actually that we have used in Fourier-Bessel series expansion, they are aperiodic in nature and converge with time. On the other hand, if you see the Fourier transform, these basis functions actually they are periodic and they don't converge. And basis functions that we use in FBSE method, they include amplitude modulation and in the representation, because if you see the Bessel functions and they decay with time. So due to their decaying nature in the time, they actually provide this amplitude modulation in the representation. So due to that, actually, this bandwidth of the signal is a function of two modulation, amplitude modulation and frequency modulation. So if you have amplitude modulation, then that will help you to get the compact representation in frequency domain. So other point that is actually advantage the spectrum which we compute based on the FBSE and provides frequency points equal to the signal length. But in Fourier transform, that becomes half, because whatever spectrum we get, that has complex conjugate symmetry. So due to that, actually, the half spectrum is only useful. Other half is actually just redundancy. It is just the same spectrum, but it's complex conjugate of that. So, but here actually we don't use complex basis functions. They are real basis functions. So due to that, we have double frequency points. So in fact, double frequency resolution as compared to the Fourier transform. And this from where this Fourier-Bessel series expansion has come. So actually these Bessel functions, they are the solution of the differential equation. So these Bessel functions are actually obtained by the solution of the linear second order differential equation. So this is the mathematical equation for the differential equation. And when you solve this linear second order differential equation, then you will have nice solution. That is y equal to a jvx plus b by vx. So a and b, they are actually arbitrary constants, and jvx and by vx, they are the Bessel functions of first kind, order v, and this jvx is the this Bessel functions of first kind or order v, and by vx is the Bessel function of second kind, order v, respectively. And actually this the basis function, the Bessel functions of first kind, order v, they are found actually very useful for signal representation because they follow orthogonality principle. So we will focus actually in this talk signal representation based on the this kind of first order, the Bessel function of the first kind of order v. And literature actually 0 and 1 order have been studied of the first kind for signal representation. So this orthogonality principle here you can see that is actually for this first kind and order v Bessel functions, they follow orthogonality principle. That is equal. So if your alpha not equals to beta, then this integration comes out to be 0. And here alpha and beta are the roots of jvx equals to 0. And two sets of Bessel basis functions which are first kind with 0 order and first order, they have been found useful in signal representation. So this is actually when you see the signal in time domain, Bessel basis function, that 0 order that you can see, that is actually for the 0 order first kind of Bessel function, and on first 1 order first kind of Bessel function, you can see the right hand side in this figure. And here these two kind of actually Bessel functions of order 1, actually order 1 and not first kind of order 1 and order 0, they have been actually studied for various applications of signals, signal analysis, classification. And based on this, actually we have proposed a new technique for signal analysis that we will see. And this for first 0 order and first 1 order, the FBSE, these are the analysis synthesis equations. So when you use 0 order FBSE, then this is the analysis equation, synthesis equation, and corresponding the synthesis analysis can be carried out by using this equation. So AK equals to 2 upon L square J1 beta K square. and the summation n equals 0 to n minus 1 n un j0 beta k n upon capital N. So this is the analysis corresponding to 0 order. Similarly, this is the synthesis equation for one order of the first kind of FBSE expansion. And for that, actually, synthesis process, analysis can be carried out using this mathematical expression. This is for one order and first kind of FBSE expansion. And here in both expressions, 0 order and 1 order, this alpha k and beta k, and these are actually beta k and lk. They are the roots of these 0 order and first order Bessel functions, and that these roots actually we have computed these roots using Newton-Raphson method. Based on this Newton-Raphson method, these roots are computed, and it has been derived based on the Taylor series approach. So based on the Taylor series, this Bessel function of 0 order J0A can be written in this mathematical way by using this mathematical expression based on the Taylor series expansion, and which solution is given by this expression. And then actually based on this relation, we have computed all roots of this J0 equals to 0, and initial root actually is assumed equals to 2, and other initial value like they have selected chosen based on the this relation beta k equals to k pi. So the first root is 2, and second root we go for 2 pi, and third root we go for 3 pi, like that, and then that basis, and finally the actual root has been computed using Newton-Raphson method. And there is actually we have derived also relation between order and frequency, and the order k of the FBSE coefficient, the corresponding continuous time frequency, that is in hertz, are actually related by the following mathematical expression, that is beta k equals to 2 pi fk capital L upon fs. And we have seen in previous slide, beta k can be written as equals to k pi. So when you put beta k equals to k pi, so then this relation can be written as k equals to 2 fk capital L upon fs. So this gives you relation between order of the actually this FBSE expansion and order of the root and corresponding frequency. So this expression actually helps us to convert order of FBSE to corresponding frequency, and that way this FBSE analysis domain, whatever analysis we perform using Fourier-Bessel series expansion, that can be used for getting actually spectrum of the signal. And the plot of the magnitude of FBSE coefficient versus obtained frequency provides a spectrum representation of the signal. And based on that, we have actually proposed a new method for signal processing that we call FBSE DWT method. So we have seen earlier this empirical mode decomposition EMD method, and it has got some actually problems. It has also got some issues like this whatever intrinsic mode functions IMFs we obtain using EMD method, they have mode mixing problem. So like this one IMF can have actually more than one frequency component, so that the different frequency components are presented particular IMF. So that actually, and another problem that is lagging actually mathematical representation. So motivated by these two major problems, recently actually empirical wavelet transform has been proposed in the literature. So in empirical wavelet transform, that is actually, it is a combination of two methods. One is empirical mode decomposition kind of approach and wavelet transform. Empirical mode decomposition, we have seen we are doing maxima and minima picking in actually time domain. Here in empirical wavelet transform, this maxima and minima will be obtained based on the Fourier spectrum. So like we take signal and then we go for the spectrum, and from the spectrum we determine maxima and minima, and based on that actually we select the boundaries. We determine the modes of the signal. We determine the boundaries, and based on the boundaries we determine we design the filters, wavelet filters, and then we separate the components. So this empirical wavelet transform separates actually these components or intrinsic mode functions from the frequency domain, and that frequency domain is based on the Fourier transform. So what actually we have done in this work, we have represented this Fourier transform based spectrum with the help of this FBSE based spectrum, and then actually we can apply this boundary detection method, filter or wavelet design on this FBSE based domain. So this, what is the motivation for that, for doing all these things? So this EWT actually fails to represent closely spaced frequency components in the time frequency plane. And also for short duration signal, there is a resolution problem in the Fourier transform. And we have seen in the earlier slides that the FBSE method has double frequency resolution. It gives you double frequency information as compared to Fourier transform, and it is suitable for short duration signal because this Bessel function decay with time, so it converges faster than the Fourier transform. So due to all these reasons, we have actually replaced this conventional Fourier transform based spectrum with the help of FBSE based spectrum. So this is actually one example. Here you can see the Bessel function, and when you see the spectrum using this Fourier transform, then it has spread here. And when this is the Fourier domain, you have band of frequency. On the other hand, if you go to FBSE domain, Fourier-Bessel series expansion, and there you can see nice, only one coefficient is required to represent the signal in the frequency domain or Fourier-Bessel series expansion domain, FBSE domain. And based on the order and frequency relation, we can convert this FBSE versus order plot into FBSE magnitude of FB coefficient versus frequency. That gives you the spectrum. So here you can see this is a Fourier-Bessel spectrum, and this is your this FBSE based spectrum. So FBSE based spectrum is more compact than Fourier based spectrum. So this is actually now framework, proposed framework, which is for FBSE WT transform. And here you need signal. Then we apply, we obtain a Fourier-Bessel series expansion based spectrum. And then we got scale space representation of FBSE spectrum. Then we determine boundaries in Fourier-Bessel domain. And from these boundaries, we determine filter banks corresponding to this FBSE method. Then we have various like different subband, for example, capital and subbands. Then we apply in the conventional empirical Wavelet transform, this Hilbert transform has been applied for obtaining amplitude of instantaneous frequency. But in this work, actually, recently normalized Hilbert transform has been proposed. So instead of Hilbert transform, we have used normalized Hilbert transform. And normalized Hilbert transform gives you more accurate instantaneous amplitude and instantaneous frequency as compared to the Hilbert transform. So that due to this reason, we have applied normalized Hilbert transform in order to compute instantaneous amplitude and instantaneous frequency. And when you have instantaneous amplitude and frequency computation of all these subbands, then actually this arrangement of this IA and IF functions provide you time frequency representation based on FBSE WT method. So this is actually one example based on the synthetic signal. And here you can see this is the first example here. The signal, this is actually sum of three AM signal, amplitude modulated signal. So here we have considered actually various cases, case 1, case 2, case 3, and where this frequency is actually their separation is increased. Like in first case, they are very closely spaced. F1 equal 9 Hertz, F2 equal to 10 Hertz, F3 equal to 11 Hertz. In the other case, they are a little bit, their space is increased. And third case, space, more spaces actually has been studied. So this separation is like 3 Hertz between the frequency components. And these signals you can see in time domain. And when you go for this boundary detection in the Fourier domain, then you can see this is actually in case 1, case 2, case 3. And here you can see the spectrum. And in case of 3, you are able to separate, actually design the filter banks. In the first 2 cases, you are not able to do that when you are going for conventional Fourier transform. On the other hand, if you go for Fourier-Bessel series expansion based domain, FBSE domain, there you can see in case of second and third, in both you are able to design the filter bank. So that actually that improvement that can be considered improved version of the spectrum in order to separate the components that we have explored in this FBSE DWT method. So these are the actually mathematical equations for scaling functions and empirical scaling function in empirical wavelet transform. And these actually, based on that, we have designed these wavelets and to separate out these signals from the different boundaries. And this here, you can see the time frequency representation of this considered signal. And this is the expected time frequency representation. So that is actually because these signals, whatever we have considered, they are synthetically generated. We are generated from our side. So we know that it's time frequency, actual time frequency representation. And second plot, this is the actual time frequency representation obtained using Hilbert-Huang Transform, HHT. And here you can see this whatever this frequencies, time varying frequency have detected, and they are not corresponding to actual frequency component. So this is not giving good detection of the frequency component, proper estimation of the frequency, or the proper actually you are not identifying them properly in the HHT method. When you go for empirical wavelet transform method, then you can see in case of third, when these frequency components are actually nicely separated, well separated, then you are able to separate them, identify. Otherwise, in first two cases, you are not able to separate them. You are not able to identify them. But on the other hand, if you go to our method, that FBSE DWT method, then you can see in the case second and case third, in both you are able to identify these three frequency components properly. And that we have also actually, this is based on the visual representation, but same thing actually, we have also seen based on the mean square error, because this is a real the synthetic signal. So we know the actual signal and it's estimated. And then you compare this mean square error for the case 1, case 2, case 3, and then between the time frequency representation. And then FBSE DWT method, EWT and HHT method. And FBSE EWT method for this actually case 2 and case 3, it provides less mean square error. And so it's justified that actually this proposed method gives you better detection of the frequency component and time frequency domain. And after that, we have considered actually
Sorry for the interruption. Sir got disconnected due to internet problem. Please be wait a while.
Hello, good afternoon.
Yes, sir.
Yes, yes.
We can hear you, sir.
Yeah, I am sorry for this actually inconvenience. There was some problem. Now again, actually power is on. So just I will share my slides. Slides are visible to you?
Yes, sir. Slides are visible, sir.
Okay, thank you very much. Thank you. Okay. So we can see here actually this one example of EEG signal, and that actually has spikes. This is epileptic seizure EEG signal. And when you see the time frequency domain, this is based on the Hilbert-Huang transform. It shows only low frequency component present in the signal, but this signal has actually both kind of frequency component, low frequency as well as high frequency components. So these high frequency components are not resolved with the help of Hilbert-Huang transform. But when you go for this empirical wavelet transform, which is based on the conventional Fourier transform, here you can see this is the spectrum, Fourier spectrum, and this is actually a segmented spectrum, bound detected boundaries, and these are the design filters. And this is the obtained time frequency representation using empirical wavelet transform. And here you can see here also you are not able to see the high frequency components present in the epileptic seizure EEG signal. But when you apply this Fourier-Bessel series expansion based empirical wavelet transform, and then you can see you have nice actually dense spectrum, and you get various detailed filter banks, and nicely you can resolve this low frequency as well as high frequency component present in the signal. So that is the beauty of FBSE DWT method. And after that, actually this FBSE DWT method we have explored for the diagnosis of actually glaucoma using this fundus images. So this glaucoma detection for this purpose actually we have extended this FBSE DWT method that is for one dimension, that whatever you have seen, into two-dimensional Fourier-Bessel series expansion based empirical wavelet transform. So let us see this glaucoma, what is this glaucoma concept actually. And this is actually development of glaucoma. It is actually here you can see healthy eye. So there's a flow of aqueous humor through the drainage canal. And when it is development of glaucoma, then actually this drainage canal blocked and this buildup on the flow fluid. And due to that, there is increased pressure and it damages blood vessels and optic nerve. And this actually, so due to that is this communication breaks between the central nervous system and this blood vessels up to the optic nerve. And due to this actually, you can see this disease is one of the actually major reason for blindness. And we go for fundus images for diagnosis of glaucoma. And when you go to doctor and they actually take over this with the fundus camera, they get this images, fundus images. And based on the this normal cup size, increased cup size, they detect the glaucoma disease. And here you can see in healthy case, this is normal cup size. And when you go for glaucoma case, this cup size is increased. And that is actually, that is also run by neuroretinal rim NRR. And in this actually, this is another INST rule actually they apply. These doctors, this fundus image divided into 4 regions. And that is inferior, nasal, superior, and temporal, according to this rule, INST rule. And based on the actually manual processing, they identify the glaucoma disease. The first and actually important features for detecting glaucoma are an optical cup to optical disc ratio, that is known as CDR, and neuroretinal rim, NRR. And if person actually is suffering from glaucoma, then the CDR actually increases and NRR decreases. And these values here, the CDR and NRR values for a healthy eye, which is around 0.3, and it is more than 0.1. And on the other hand, the CDR values actually are between 0.5 and 0.7 for moderate glaucoma, and it is more than 0.7 for severe glaucoma. And here you can see actually in this figure, these days, this fundus images, and there is a lot of interest in the literature to develop this computer-aided medical diagnosis tools. Even people are developing these algorithms which are based on the signal processing machine learning algorithms. They can be implemented in the smartphone, and the smartphone will become really smart. And nicely, it can detect actually glaucoma at early stage. So it has got a camera, and then fundus images will be taken, then the signal processing will be applied, then you will have nice subband images, then we extract features, and based on the features, we classify them, automatically classify, and this warning system can be developed, and nicely with the help of this computers, laptop, mobiles, these algorithms can be implemented real time, and warning can be given whenever this glaucoma disease is initiated. So at the beginning level, one can detect this glaucoma based on the fundus images. So there is actually people are trying to develop various signal processing machine learning based methods for the development of automated systems for the identification of glaucoma in real time. So glaucoma can be broadly divided into 2 types. So first type is open angle glaucoma, and second type is angle closure glaucoma. And open angle glaucoma is actually most common type of glaucoma, and its symptoms cannot be detected early, and it develops progressively due to insufficient drainage of fluid out of the eye. And if it is not detected in the early stage, then it can cause gradual loss of vision. And in this work, actually, we have studied open angle glaucoma. And angle closure glaucoma, it is rarely found, and also known as narrow angle glaucoma. And actually, this is due to sudden blockage of drainage system of eye, and which results in acute pain, bad eye, and immediate loss of vision. So for this talk, we are focusing on open angle glaucoma. And in this work, actually, we have proposed two-dimensional Fourier-Bessel series expansion based empirical Wavelet transform method for image analysis. And we have compared zero order two-dimensional FBSE method and first order two-dimensional FBSE method for this diagnosis of glaucoma based on the fundus images. And two-dimensional FBSE method has also been studied in the multi-frequency scale framework. And we have actually studied for automated glaucoma detection for the fundus images based on the 2 approaches. One is conventional machine learning method, and second one is convolution neural network. So this conventional machine learning method, actually we extract features from the images, and then these features we use training and testing kind of system, and that is actually traditional. That is recently the features are extract learning from features also can be learned from the image itself. That is like CNN, deep learning, such kind of actually machine learning tools are coming. We have also explored them. So this two-dimensional Fourier-Bessel series expansion based DWT method. So what actually we do, we first we compute average row and average column FBSE spectrum. So for example, this is the fundus image or any image. Then you apply FBSE row wise, and then you perform average over this column wise in the FBSE domain. And then this gives you the average row spectrum, average row FBSE spectrum. Similarly, what we do for column, we go for the image and we apply FBSE column wise, and then we apply this averaging over row wise. So it gives you the average column FBSE spectrum. Then this earlier we have seen this order 0 and order 1 FBSE spectrum or based analysis synthesis process. So these are the mathematical equations for the synthesis process of order 0 and order 1 FBSE method. And these are the actually analysis expressions for this is the first one is for 0 order and second one is for first order. So in these two actually approaches we have studied and we have compared 0 order and first order FBSE approaches to in the FBSE DWT method. And once you have FBSE spectrum, then it can be according to that presented that we can perform boundary detection on the average row and average column spectrum based on the scale space approach, and we can design corresponding filter bank. And scale space approach, this is actually here we consider spectrum as histogram, and a spectrum actually can be considered like indication of the occurrence of particular frequency within the signal. And the scale space operation is also actually like a smoothing operation. Here you can see this is like a image and then convolving image with the Gaussian filter, and Gaussian filter that is expressed with the following mathematical equation, and that is actually one kind of smoothing filtering process. And once you have done this smoothing, and this where this parameter C, this is between 3 and 6, based on this this m equals to C under T plus 1, and this is constant that is equals to 6. And the smooth spectrum, these boundaries we have detected using maxima minima approach and minima between two consecutive maximas. So here you can see this is the actual toy image, and these are the average row spectrum, and this is actually based on the Fourier-Bessel series expansion, and this is based on the Fourier transform based representation spectrum. So you can see this Fourier-Bessel series expansion based average row spectrum gives you better boundary detections as compared to the Fourier based this average row spectrum. And similar to earlier, these are the actually mathematical expressions for the empirical scaling function and empirical wavelet functions for designing actually wavelets in order to separate these subband images from these fundus images. And this is these are the actually when you use Meyer's wavelet, then these are some constraints that you have to satisfy, and in order to design tight frame of the scaling function, wavelet functions, and we need to take care of this condition. And here you can see this order 0 and order 1 two-dimension FBSE DWT methods. So this is actually RGB image after resizing. So this is in the literature actually this green channel has given better performance for diagnosis of glaucoma. And when you have image, fundus image, you can decompose this into 3 colors: R channel, R or green, and this B and blue. And this green channel has given better performance. So due to this reason, we have selected green channel. And here you can see for this green channel, this is the RGB image. And after this the green channel, this is enhanced version. Pre-processed. So sometimes you have unwanted actually components present in the image that you can actually, with the help of pre-processing, you can remove them and you can enhance the image for further processing. So this after that, this is the average row spectrum and average column spectrum for 0 order FBSE EWT method. And similarly, it's average row and average column spectrum for first order FBSE EWT method. And from the actually, these are the designed corresponding design filter banks for average row spectrum, average column spectrum for zero order FBSE EWT method. And these are the designed filters for first order FBSE EWT for a two-dimensional version for the average row spectrum and corresponding to average column spectrum. And in this work, actually, we have selected number of boundaries, that is selected 1. So there will be total 4 subband images will be there. And here you can see this is the order 0 two-dimensional FBSE method. These are the obtained 4 subband images. And this bottom one, this shows the 4 subband images. They are obtained using order 1 two-dimensional FBSE method. So once you obtain these subband images, then we have also actually studied the effect of scales. So like when you have a spectrum, then you consider entire spectrum. You can also consider half spectrum. You consider the quarter, different the half of the half spectrum. So we call them scaling operation. And in the first, you can see this is actually average row spectrum here, and at full scale. This is the average row spectrum at half scale, and this is the average row spectrum at quarter scale. And these are the right hand side, you can see the design filter bank corresponding for all these scales, like full scale, these are design filters, and for half scale, these are design filters, and quarter scale, these are the design filters. So, and then these filters, they can separate out these subband images for the different scales, and that you can see here. So this example shows the obtained 4 sub images for full scale. That's the first row. And second row, we can see the 4 subband images. They are obtained at half scale. And third row shows the 4 subband images obtained at quarter scale. So in that way, these all scales actually we have obtained different subband images. And this is the proposed method where we use this conventional machine learning method, where we apply this signal analysis technique, and we obtain the subband signals, and then we extract features from them. Then we apply these features to machine learning methods for performing classification. So same actually framework we have studied for this glaucoma diagnosis based on the fundus image. So you have here green channel, this fundus image. Then we have applied pre-processing. So it will enhance this green channel fundus image, which makes suitable for further processing. And once you have this pre-processed image, then we apply two-dimensional Fourier-Bessel series expansion based empirical wavelet transform, which will give you 4 subbands for each image. And then we extract features from these subband images, and then we perform feature selection. And because all features, whatever we obtain, they are not relevant, and only few of them actually are significant. And then so it has actually, it improved the classification performance, and also it helps us to implement this classification process in real-time manner. So it has some advantage. Due to that, feature selection has its important role. And after that, selected features have been given as an input to classify, and which will automatically classify this fundus image, either belongs to glaucoma or belongs to healthy class. So in that way, this automated classification of this glaucoma can be done based on the fundus image and an input to this framework. So for this study, we have used data set, that is data set RIM1, R1, RIM1, R2, RIM1, R3, the STGS, Origa, and this different database has different image counts. Like for the RIM1, glaucoma 51 images, healthy class 118 images, total 169 images. So each actually data set has got a different number of glaucoma fundus images and different number of healthy fundus images. So this gives you a total fundus images. And in order to extract features, we have extracted gray level co-occurrence matrix, GLCM features, movement inversion features, and histogram based features. And this total, in this way, we compute 116 features. And here you can see this table shows the mathematical expression for GLCM features. And similarly, movement inversion features that actually we have computed for the subband images that obtained from this two-dimensional Fourier-Bessel series expansion-based empirical wavelet transform. And third set of features, they are actually histogram features. So these actually three set of features we have computed from the subband images, and we obtained from the fundus images. And this for feature selection, we have applied principal component analysis based method. And here you can see this cumulative variance versus this number of principal components have been plotted. And for the 13 principal components, we can see this plot gives you 90% cumulative variance. Similarly, this is for order 0, two-dimensional FBSE method, and for one-dimensional order 1, two-dimensional FBSE method, the number of principal components are 9 in order to have 90% is cumulative variance. So these many principal components have been selected instead of all principal components, so that actually this feature selection has been done based on this principal component analysis method for order 0 and order 1 two-dimensional FBSE methods. And this is actually performance measures in terms of percentage of the proposed methodology based on the support vector machine classifier, multi-layer perceptron classifier, least square support vector machine classifier, and random forest classifiers. So here you can see for order 0 and order 1 case, and for the different data set studies using SBM classifier for R1, R2, R12. And this table shows the performance measures in terms of accuracy, sensitivity, specificity in terms of percentage. And similarly, we can see the performance in terms of percentage for accuracy, sensitivity, specificity for R1, R2, R12, these databases using multi-layer perceptron classifier. And this table shows the classification performance in terms of accuracy, sensitivity, specificity based on least square support vector machine classifier for the different databases R1, R2, R12. And then you can see based on the random forest classifier for the different databases R1, R2, R12, and we obtain accuracy, sensitivity, specificity in terms of percentage. And based on these, actually, when you see these results, and then we found that random forest classifier actually is performing better in all classifiers, and that is followed by the SVM support vector machine, multi-layer perceptron, and least square support vector machine classifiers. And order 1 two-dimensional FBSE method is better than order 0 two-dimensional FBSE method. So after that, this figure shows the error wire plots of the average performance measures corresponding to R1, R2, R12 databases. And here you can see average accuracy, average sensitivity, and average specificity from the 0 order two-dimensional FBSE method. And this is for the upper one, and lower one shows the accuracy, sensitivity, specificity for order 1 two-dimensional FBSE method. So, and based on this 4 studied actually this classifiers, support vector machine, multi-layer perceptron, least square support vector machine, random forest classifiers. And this actually, then also we have studied Bhattacharya space algorithm, entropy, and receiver operating characteristics, ROC, student t-test, and Wilcoxon test, also studied for feature reduction process. And here you can see this error wire plots of the average accuracy. Since the random forest classifier has given better performance, so here we have shown only for random forest classifier. And this is the average accuracy corresponding to Bhattacharya space algorithm, entropy, ROC, student t-test, Wilcoxon test. And you can see the comparison. The first one is corresponding to order 0 two-dimensional FBSE method, and second one is corresponding to order 1 two-dimensional FBSE method. Then here we can see accuracy plot of various feature ranking methods. Here included PCA also, and for 0 order two-dimensional FBSE method, and for accuracy for database R1, R2 and R1. And this actually we have studied performance of two-dimensional FBSE method at full various scales that we have seen, full scale, half scale, and quarter frequency scales for R1, R2, R3, and STGS and Origa databases. And you can see the performance in terms of accuracy, specificity, and sensitivity in terms of percentage for different databases, and at full scale, half scale, and quarter scale. So different scales actually we have studied, and the purpose was to find out which scale is better for the automated classification of glaucoma disease based on the fundus images. So this is actually proposed method, second proposed method for the automated identification of glaucoma based on the fundus images. And this is based on the deep learning these days is convolutional neural network. Here we don't need to obtain features, just this is like this machine, automatically this convolutional neural network CNN, it learn features from the data itself. So here you have this green channel that is fundus image, and then we apply two-dimensional FBSE method. Then we have run 4 subband images, and then we apply this residual network ResNet 50, and then ensemble is actually computed, and then we have softmax layer, and which will classify whether this image belongs to glaucoma disease or not, or healthy. And this actually, this is here we have used transfer learning concept, and this is shows the block diagram of transfer learning that we have pre-trained process, then turn on data from new data. So this is transfer learning concept. And these deep features that actually we are extracted from the last average pool and last fully connected layer, and assembled using this maxima, minima, average, and fusion. And this experiment has been performed in full, half, and quarter frequency scales. And here you can see performance measures for order 0 and order 1 two-dimensional FBSE methods at full, half, and quarter frequency scales for this proposed methodology too, where we are using this convolutional CNN deep neural network, deep learning kind of concept. And there actually you can see this fusion when you maxima, minima, average, fusion, and different operations, different actually classification performance have been achieved. And then we have actually this is for half scale, and this one is actually full scale, and these are results for half scale in deep neural network framework. And here this is for quarter frequency scale. So here you can see different operations for ensemble, and different actually classification performance, accuracy, scientific specificity. Even we have included, you have computed area under curve, area under ROC. So these actually various performance measures have been computed and in this FBSE DWT framework. And then we have compared various conventional machine learning and deep learning methods with our proposed method. So here you can see, like in proposed method first, which is based on the conventional machine learning algorithm, where we extract feature, then we perform training of the system, then we apply this trained system we use for the classification purpose. And here actually a lot of work has been done in the literature. People have used in the various years, they have used various data, and same database we have used, and they have used various methods, signal processing and methods like complex wavelet transform, statistical features, wavelet packet decomposition, entropy, energy features, optimal hyperanalytic wavelet transform, empirical wavelet transform, and chorontropy feature, variational mode decomposition, entropy feature, discrete wavelet transform and combined feature, discrete quasi-bivariate variation mode decomposition, and here various classified artificial neural network, support vector machine, least square support vector machine. And here we have used this two-dimensional Fourier-Bessel series expansion based empirical wavelet transform, and together with random forest, SVM, and this classifiers. And its features, actually, these are the features that we have studied in our work, significant features. They are coming 9, and which gives you performance actually better than the other existing methods in the literature based on the conventional machine learning. Then we have also compared our method with the deep learning framework, and where people have this recently actually trend has been started in the literature. People are exploring these deep learning methods for this automated identification of signals. And in 2017, 18, 19, people have used this kind of methods. And the same database actually they have studied, and we have also studied same database, and our method actually has provided better accuracy, sensitivity, specificity, area under curve than the other existing methods in the literature. And we have also actually computed the required time for proposed methodology for the single image. Like this method has actually different parts, and we have seen the computational complexity for different parts is coming nearly in seconds. Like when you perform this order 0 order 2-dimensional FBSE DWT at full scale, it requires only 0.918 seconds. And so this in overall, when you combine these all methods, all parts of the method, then proposed method 1 requires computational complexity around 4.26 seconds to implement the algorithm, and proposed method 2 can be implemented in 1.64 seconds. So this actually, it shows that these proposed methods can be implemented in real-time manner for automated diagnosis of glaucoma using fundus images. So this is the actually conclusion of this talk. By using this Fourier-Bessel series expansion-based spectrum instead of Fourier transform, we get better boundary segmentation. And in proposed method 1, best results are obtained using order 1 2-dimensional FBSE DWT method with principal component analysis and random forest classifier. In proposed method 2, order 1 2-dimensional FBSE DWT method sub-images at full frequency scale with fusion ensemble model has provided better results. And the results and computational time for both methodologies indicate that the proposed methods are practically implementable. And this actually, whatever work I have presented, this is actually based on the 2 of our recent papers. And you please go through these 2 papers in order to have more details about the presented work. Thank you very much. Yeah, any questions, please?
Sir, myself, Dr. Ravi.
Yes, please.
Sir, good afternoon, sir. How are you, sir?
Good. Yeah, fine.
Sir, sorry, even though you are having a hectic schedule, you came forward and you have taken the classes. Thank you, sir. I think in 2015, I met you in IIT Indore. I came to the short-term training program. On the day we have discussed on EMD, empirical wave, I think empirical mode decomposition, EMD.
Yeah.
At that time, it was a new.
Yeah. Now people are using concept of EMD for various techniques, new techniques.
Yes, sir. So at that time, I chose an EMD. The same EMD I have applied for my research work also.
Oh, very nice.
So from that short-term training program, I have learned EMD. I applied for my research work. After that, I have published 3 papers on the
nice.
EMD techniques.
Yeah, good. Yeah.
So thank you, sir. Once again, you came forward and you have taken the session. And this type of support I am expecting you in future too also, sir. Please, sir. Please support us.
Yeah, thank you. It is my pleasure. Thank you very much. Thank you. Thank you, Dr.
Thank you so much
for this opportunity. Thank you very much. Thank you.
Please, madam, proceed.
Sir, thank you for sharing us with valuable information. Even in your busy schedule, you accepted our invitation and talked clearly about machine learning for automated diagnosis of glaucoma from fundus images. We really thank you for your wonderful session, sir.
Yeah, thank you very much. Thank you. Thank you.
Thank you, sir.
Thank you. Thank you.
I request the participants, please fill the feedback link